Hello, everybody, and welcome to another exciting episode of our weekly Cloud on Air Innovator Series. I'm Chloe Condon, a cloud advocate here at Google, and I'll be your hostess each week as we dive into different technical topics, watch demos, and learn best practices from some of our top experts here at Google. If you joined us last week, welcome back, or the week before, or the week before that. Welcome back. And if you're new here, welcome to our new online community. We're so excited to have you join us and be a part of it. Now, if you're joining us live, you may notice that we have a live chat. So feel free to use this space to interact with other viewers and ask any questions that you have about the topics being discussed in today's session. One of our moderators will try to answer you live in chat, or you may just be lucky enough to have your question answered live on the air during our Q&A session with our speaker at the end of this presentation. And if you're not joining us live, why not? Make sure to register for one of our upcoming sessions so you can join in on the fun live as it happens. To learn more, check out cloudonair.withgoogle.com, and you'll be able to take a look at our previous streams and register for all of our upcoming sessions. You can take a look at previous sessions, pop some popcorn, get comfy, or maybe take a peek at some of our upcoming ones where we'll be covering cloud topics like data analytics, GenAI, security, developer productivity, and so much more. We have a great library of content for you to look through, so feel free to check out our catalog of videos from Google experts that you can watch on demand for free. Without further ado, let's begin today's session. Take it away.
Well, hello, welcome everyone. I'll be your host for next 1 hour, and I'm really excited to talk about how you can supercharge your modern GenAI applications and LLM workloads with Google Cloud TPU. I'm an AI hypercomputer go-to-market lead, and for those of you who are wondering what is AI hypercomputer, don't worry, we'll cover it later in the presentation. So today we're going to cover a few topics. So we'll start with the overview of Google Cloud TPU, and we'll talk about our next generation systems. We'll go into more detail on training and inference on Cloud TPU. And then we'll close it up with some of the guidance on how you can proceed from here. All right, so let's get started with an overview. TPUs, they are custom-designed machine learning accelerators that provide compelling performance per dollar at scale for various workloads, including GenAI apps, natural language processing, computer vision, and recommendation system, and they leverage the leading framework and orchestration solutions. TPUs are built over XLA compiler, and they support all of your favorite frameworks like TensorFlow, PyTorch, and JAX. And throughout the generations of Cloud TPU hardware, we built these systems with one single objective, which is deliver superior performance at lower TCO and at scale. I would like to start here to give you a broader sense of Google AI capability. Our pioneering AI research and development is driven by more than 3,000 expert researchers. We have produced more than 7,000 research papers with over 2.6 billion citations. We have invented some of the most important AI technologies that fuel the current revolution, like transformers, compute optimal training, optical circuit switch networks, and even application-specific chips like tensor processing units. And our innovation extends to highly accurate and efficient AI models, such as LLMs like PaLM, Lambda, and most recently we introduced Gemini, which empower the real-world products. Our software leadership directly empowers valuable products. We have created some of the most popular open source systems like TensorFlow, Kubernetes, JAX, XLA, and we have produced, proud to say that since 2022, Google has been the largest contributor to open source, according to the Open Source Contributor Index. We have also proven expertise taking AI to production, as demonstrated by 20 plus years of our experience integrating the AI innovations into large-scale applications accessed by billions of users every day, like YouTube, Maps, Search, Ads, Gmail, Photos, and many more. Our world-class infrastructure enables the enterprises at massive scale. We operate some of the largest and most efficient data centers in the world with innovations in advanced liquid cooling techniques, optical interconnect, and dense data centers in many regions. Customers capitalize on our infrastructure leadership to quickly deploy AI solutions and products reliably, securely, and with high scale in a sustainable way. AI is in our DNA. We're fortunate to be able to work with thousands of customers across many industries to help them leverage AI and transform their business. Google is the platform of choice for startups building Gen AI solutions, and more than half of the funded Gen AI startups, they are Google Cloud customers, including 70% of the most innovative Gen AI unicorns that are building their solutions on our platform. Customers like Anthropic, AI2, Runaway, ML, Cohere, Character, and many more use GCP to train and serve their Gen AI models and build innovative products from AI chatbots to advanced video editing capabilities to marketing tools and many more. So we're building the industry's most advanced AI cloud platform by listening to our Gen AI user needs. And there are three main types of customers or users as we see. First one is the foundation model producers. They need best training speed and leading AI frameworks. Foundation model tuners, they also need speed and ability to easily integrate their data and storage. And finally, the foundation model consumers, which need low latency serving and best cost per inference. So we have built this most comprehensive AI infrastructure, which is designed to meet the needs of every AI workload and for every customer type. So working from the bottom up, it starts with the leading TPU and GPU accelerated compute options, complemented by a range of AI optimized storage and data integration solutions. We bring this all together into a supercomputing system with scalable networking, state-of-the-art water cooling data center, and much more. And we make it all easy to consume with support for both GKE and GCE. And we deliver unique value in software, enabling training and serving of workload across multiple systems, complemented by an open, high-performance framework, compiler, and more. And finally, with Vertex AI, we make it easy to integrate and serve Google models and partner models in your applications. We recently introduced AI Hypercomputer, which basically is a full stack of AI optimized hardware, software, and consumption models. It's actually a supercomputing architecture that consists of three things. First, performance optimized compute, storage, and networking over our ultra-scale data center infrastructure. Second, software-tuned, optimized, and dynamically orchestrated AI training and inference. And third, flexible consumption models and dynamic resource scheduling. What's exciting about this AI hypercomputer is system-level productivity. So as the scale of Gen AI increasing and it demands efficiencies, but in traditional way, it's done in a piecemeal component level enhancements, which can lead to many bottlenecks. AI hypercomputer employs system-level core design to boost the efficiency and productivity across AI training, tuning, and serving. AI hypercomputer enables faster and more scalable Gen AI model training and serving, allowing the new products and capabilities to reach your customer sooner. So Gen AI models, they are rapidly becoming more sophisticated and capable. They are enabling enterprises across a wide range of industries to solve very complex problems and uncover new opportunities. However, as Gen AI models have grown in size and complexity, so have their training and inference requirements. Large models up to hundreds of billions of parameters can take months to train on specialized hardware. In fact, the number of parameters in LLMs has grown by more than 10x every year in the last 5 years. As a result, consumers need AI optimized infrastructure that is both effective and scalable. And in addition to the specialized hardware, customers still need access to a fully integrated AI stack with storage, networking, software, and framework which are optimized for AI workloads. So there comes our exciting launch of our 5th generation cloud TPUs. So we have been building TPUs since 2015. The first TPU was built in version 1 was built in 2015. But as you can see on this slide, we have continued to release faster and more performant generations of TPU. Last year, we announced the general availability of Cloud TPU v5e, which is our most cost-efficient TPU to date. And we also announced last year public preview of our Cloud TPU v5p, which is our most scalable and powerful TPU. So let's get into the details of our Cloud TPU v5p, which is in preview. As I was mentioning before, it's our most powerful TPU to date. v5p can be leveraged to compress AI model development time from months to weeks. It's 2.8x faster at training LLMs than the previous generation. And with our second generation sparse course, training embedding heavy models is 1.9x faster. TPU v5p is more scalable as well. In fact, it's 4x more scalable than previous generation. And it offers state-of-the-art optical circuit switching technologies that enables the world's highest bandwidth interchip interconnect at 4,800 gigabit per second with a 9K ICI chip domain. And in addition to being powerful and scalable, it's highly flexible as well. So it can enable training on a diverse model architecture, such as LLMs, mixture of experts, recommendation system, and many more. And it features 3x more high bandwidth memory, which makes it a very versatile enabler of workloads that otherwise would be memory constrained. So TPU v5p is a marvel of engineering. In each pod, it features 8,960 chips, is 960 chips. And by using our multi-slice technology, we can achieve impressive scale, enabling training workloads to tens and thousands of chips. And with higher bandwidth, v5p accommodates large batch sizes. And as we have demonstrated here, it speed up the GPT-3 175 billion parameter model training by 2.8x over the TPU v4, which is the previous generation TPU. We also have TPU v5p, which is generally available and is focused on providing the most efficient and versatile offering. So let's take a look at what v5e offers. So essentially offer three things. One is the cost efficiency, it's versatile and scalable. So TPU v5e provides 2.3x higher performance per dollar when training large language models and 2.7x higher performance per dollar for inference as compared to the previous generation TPU. And in addition to running both training and inference, TPU v5e comes in 8 different VM shapes, which allows you to choose the optimal shape to suit your AI model. So what does it really mean? It's three things. Train and serve faster, more affordably, and more productively on v5e. So when we look at the architecture, of course, v5e is not the largest TPU that you have seen to date, but it is the most efficient TPU to date. And in a world where we're confronted with the global AI chip shortages, we have changed the way we think about serving our customers. So we have chosen to make every chip count. Recently, we actually did a very impressive experiment to scale one of the world's largest distributed AI training job, which spanned 50K, more than 50K TPU v5e chips. And we achieved this by virtue of a few things. One is our incredible multi-slice software, deep integration with GKE, and also leveraging accurate quantized training library and in precision format, which we'll cover later in the detail. And here are some of the specs and speeds across our 4th and 5th generation at a glance. So you can see how significantly we have been able to scale the TPU v5p and pod over the prior generations and improve the chip efficiency significantly. So a single ICI domain of a TPU v5p pod contains almost 9K chips, delivering 459 teraflops of BF16 or 918 teraflops of Int8 with 95 gigabits of hardware memory on each chip. So it's a really mega powerhouse platform for giant training workloads. On the other hand, V5E is our most cost-efficient system, and it basically enables your dollars to go further when it comes to training and serving your production workloads. And with each of the fifth generation system, we actually heavily invested into the complementary software stack. From leading AI frameworks such as PyTorch, TensorFlow, and JAX, now you can train and serve your model end-to-end on TPU. So what you train is what you serve. And TPUs are also integrated with GKE, which enables seamless workload orchestration, and integration with Vertex AI brings the fully managed training and prediction workflow. So this combination of elegant hardware and out-of-the-box software provides a cost-efficient and productive end-to-end AI development platform. A diverse number of our customers for different use cases, they are leveraging our fifth generation TPU to power their state-of-the-art AI modeling use cases. These are some of the customers, but we have many more that are leveraging our platform. I'll just highlight one here. So with the launch of Gemini state-of-the-art language model, our very own Google DeepMind and Google Research, they have emphasized that how TPU are vital to enabling their largest scale research and engineering on cutting-edge models like Gemini. All right, so now let's take a look at how large-scale training is enabled on Google Cloud TPUs. So in this section, we're going to cover a few things. So first of all, we'll try to understand that what are the underlying unique factors about the TPU architecture, which is powering this unique acceleration and performance per dollar benefits we talked about earlier. We'll also look at the orchestration, and finally, we'll double-click a few details such as Int8 optimized training on TPU and accurate quantized training library. So when it comes to domain-specific architecture, the basic principle we have taken here is keep the hardware simple, offload the heavy work to software. So just drawing up comparison here in contrast to the GPU-based systems, which have thousands of CUDA cores and hundreds of streaming multiprocessor, TPU systems have actually very few but very large matrix multiplication systems, which basically accelerate the typical computation which we see in the deep learning workloads. And furthermore, there are specialized components which are designed for the acceleration for large-scale ranking and recommendation systems, which really have large embedding tables, which have to be sharded across multiple chips. So if we go out of the chip level and go down to the system level, one thing which really set apart TPU is chip-to-chip interconnectivity, which is called the ICI link. So basically, when a chip is connecting or communicating with another chip, it doesn't use the host internet. It actually uses a very high bandwidth optical ICI network. So one of the reasons, and that is one of the reasons that TPU can scale really strongly within a single ICI domain, which is basically defined by the fixed number of chips within an ICI mesh. What you're seeing in the middle diagram is that for TPU V2, V3, and V5, we have two-dimensional ICI mesh. But for TPU V4 and V5P, we have a three-dimensional dimensional mesh with 4x4x4 building block, which have then a wraparound link to provide the maximum bisectional bandwidth. We also actually recently introduced a technology that let us scale beyond a single ICI domain. So within the ICI domain, I just talked about, we have the chip-to-chip interconnect, but what really helps us scale impressively is this multi-slice technology, because it helps us scale beyond the single ICI domain. And putting this all together is our software stack, which is powered by XLA compiler. So what is crucial to know about the XLA compiler is that in contrast to the GPU system, where people write the customized CUDA kernels and do the optimization. In the case of XLA, it's actually handled by the compiler. So in this way, and all those optimized kernels are actually generated by the compiler. So in this way, you're set for success right out of the box with easier scaling experience on the TPUs. So no matter which framework you're using, whether it's PyTorch, Tensor, JAX, your computation is actually expressed in terms of a computation graph. And this graph is then compiled by the XLA compiler, and it goes through a series of optimization processes. And XLA can see both the computation as well as the communication between the chips, which are there in the graph, and it generates those optimized kernels I was talking about earlier, which then run on a very simple TPU hardware in a distributed fashion. So one of the key takeaway is that at framework level, yes, there are some unique capabilities in different frameworks, but when it comes to executing a computation graph and doing optimization on that computation graph, these capabilities are very similar across the three frameworks in the way the XLA compiler handles it. So let's take a look at how we take this actually, and you're running your training workload on TPU. So what I'm showing here is a 16-chip TPU slice. So there are 16 TPU chips in this ICI mesh, and there are corresponding set of VMs, which basically are not much different from the GPU VM, where we have a set of accelerator chips which are connected to a host VM via the PCI. But the difference here is, as I was mentioning before, the chips can actually talk to each other on this high bandwidth ICI link, which exists between the chips. So the way you interact with the system is that you have your own training script, which defines your training environment. You submit that via SSH, and then you run the job. That's simple. All right, so let's talk about performance on the training side. So here we are showing the flop utilization for a 32 billion parameter dense model, and also for 175 billion GPT-3 model. So there are three bars here which shows BF16 and int8 training. Int8 is mixed precision training, and we used actually our accurate quantized training library, and we were able to convert a subset of matrix multiplications which are run during a typical training cycle with the int8 precision. And by doing so, we were able to accelerate the training step time further, but more importantly, we did it without any significant negative impact on the convergence itself. So with these capabilities in conjunction with the multi-slice port, we have been able to scale to a really large number of chips. So this chart is from our TPU V5 eRun across 50,000 plus chips, and we were able to get upwards of 50% model flop utilization. So let's talk about int8 a little bit here. So some of you are thinking that int8 training would require more steps to convergence. So how can it enable the faster time to resolution? With our latest solution, we're seeing only less than 5% more steps to solution, while boosting the number of steps per second by 25%. So this chart shows the training loss curve for an 8 billion parameter model using int8 and BF16, and the loss curve is virtually indistinguishable. And furthermore, training with the AQT, it produces an already quantized model. So if you have to serve that model, there is no extra work needed, which goes back to the earlier remark: what you train is what you serve. Here are some of the customer testimonials. So this customer Salesforce, as you can see, this Salesforce is already seeing significant gains for pre-training their workload using JAX on TPU V5P. We have another customer. This is a customer on our TPU V5E. For them, TPU V5E was able to deliver 1.9x more performance per dollar on fine-tuning Falcon 7B and Falcon 40B training workload. All right, so we talked about TPUs, we talked about how the training is done on TPUs. Now we're going to talk about how the inference is done on TPUs. So let's take a quick step back and talk about why we are excited about inferencing. So we know the world's demand for GenAI, machine learning, compute, and for large language models is growing exponentially. And those training jobs are very compute intensive. But if you think about it, once you have trained and fine-tuned your model, what comes next? Well, you want to serve this model to millions of users, and if you're successful, potentially to billions of users. So in time, actually, the demand for the inferencing compute is going to outpace the demand for training compute. And that is why we are so excited to talk about what makes TPU great for LLM and other GenAI inference use cases. So the key takeaways on takeaways on this slide are their TPUs are highly efficient, scalable, and versatile. So we'll talk about the performance efficiency in a bit, but on the scalability side, you can serve the largest and most demanding Gen AI and LLM models with up to 2 trillion parameters without sacrificing performance. They're highly versatile. We support all of your favorite frameworks, JAX, PyTorch, Tensor, and we integrate with GKE for orchestration and autoscaling, and integrate with Vertex AI to provide capabilities, including prediction services. So let's talk about the performance here. When it comes to inference, V5V actually demonstrated 2.7x higher AI inference performance per dollar with higher throughput per dollar and low latency across multiple models like Llama, GPT, and Stable Diffusion. And this comparison is to our previous generation TPUs. And in addition to throughput, of course, latency is an important factor for the AI-powered applications because you want those applications to be responsive to your user requests. And on the latency as well, we have done a lot of hardware and software optimization, and we're able to achieve 1.7 times speed on TPU v5e compared to our previous generation. All right, so we're going to take a closer look at one of the most popular open source model, Llama 2 from Meta. It's actually a family of model ranging from 7 billion parameters to 70 billion parameters. And the largest 70 billion parameter has 8-way model parallelism, which is really interesting architecture feature and has low query attention. So it's a fantastic benchmark for LLM inference performance, and it really put accelerators to test. So let's take a look at how V5E did on this compute-intensive workload for inferencing. So as you can see here, for the largest 70 billion parameter, um, increasing the batch size from 2 to 16, throughput goes up. So we start with the 7 tokens per second for at a chips as a batch size of 2, and we go all the way to 34 tokens per second at a batch size of 16. And this is expected because as you increase the batch size, you make more use of the accelerator, so your throughput goes up. But that's not all. When you apply the optimization, such as the quantization, you can even get more performance. So the blue bar shows the throughput for BF16, and the green bars show the performance numbers with int8 quantization. So as you can see that with those additional optimization, you can go even further. And with a batch size of 32 with int8 quantization, you get 42 tokens per second per chip. That is an impressive number. And it's very competitive with other inference solutions that are out there in the market. And we talked about the latency as well. So with TPU v5e, for the smaller 7 billion parameter, you can get latency as low as 3.5 milliseconds per token. And as we increase the batch size, the latency increases, that's obvious, but it actually doesn't increase linearly. So for a 70 billion parameter model, the latency only goes up to 10.6 milliseconds per token. Which is again very competitive with the other comparable solutions. All right, so let's bring it all together. We saw the improvement in performance, improved throughput, reduction in latency. So what does it mean what does it mean to you? Well, the number one request we get from our customer is that I want to serve at the largest scale possible with the lowest cost possible. So in this chart, we're measuring the dollar cost of serving 1,000 tokens of Llama 2. And as you can see, the numbers of different model sizes. So for a 7 billion parameter model, you can serve 1,000 tokens with as less as 1.5 cents. So what this translates is you can serve 1 million token of Llama 2 7 billion for $1.50. And this pricing is based on 3-year discounted pricing. These are very, very compelling performance results. And this is something that really enables serving AI models and other use cases at a very large scale economically. All right, so let's take a look at the V5E inference. We talked about the hardware, but let's take a look at the software stack, which makes all this inferencing amazing performance possible. So we're going to start on the left-hand side. So on the left-hand side, you have your model, which is trained in one of the open popular frameworks, PyTorch, TensorFlow, JAX. We export this model into a safe model format, which essentially is a serialized representation that allows additional optimization in a framework agnostic way. We then take this save model and run it through our TPU inference stack. And TPU inference stack does few things. Well, first of all, it makes the model compatible with TPU. Second, it applies some key optimization. And one of the most important one is quantization, which I talked about previously, and we saw great performance improvement with using quantization. So if you use, instead of BF16, if you quantize your weights, you can really see some significant performance gains on the same hardware without actually any more chips or compute power. And this is all handled by the inference converter. So at inference converter, you can do the optimization with intake quantization. And it also does some additional optimization, and one of them is partitioning. So GSPMD partitioning basically allows tensor and data parallelism, which will be then handled by XLA compiler. All right, so we move to the XLA compiler. We have a TPU compatible model coming out of the inference converter, and now we're going to run it through the XLA compiler, which is going to do its magic. It also does XLA compiler a number of optimization, including high-level fusion, low-level scheduling, hardware-specific optimization specific to TPU. But one of the kind of important feature is it also distributes the model across multiple cores to enable the data and tensor parallelism that was we talked about in the inference converter. So finally, coming out of the XLA converter, you have a TPU compatible model, which is highly optimized, and you can serve it using a variety of inference servers and stacks of your choice. So we have the support for TensorFlow serving. We support Torch Serve. We also have support for Ray Serve. And we also support JAX, that was actually developed by Google Research and Google DeepMind. It's open source. And it includes some key optimizations and has great support for quantization we talked earlier. In fact, the MLPerf 3.1 submission for inference, we actually used SACs for those submissions and demonstrated amazing results for performance per dollar on TPU. So let's briefly talk about the scalability aspect. So smaller models like Llama 2 7 billion, 13 billion, you can run efficiently on even a single TPU V5E chip. But of course, you can scale up. For instance, Llama 2 70 billion, you can scale it up to 16 chips. And then the larger models with trillions of parameters, you can scale it to 256 chips within the single ICI domain. So the key point here is that you can choose the TPU shape that is best suited for your use case, and is optimized and does not unnecessarily use resources. But of course, you can easily scale up without any code changes to run your code on large number of chips to get additional scale factor. So let's take a look at some of the customer use cases for inferencing on TPUs. So on November 8, we announced the general availability of TPU v5e. On this same date, this article was published in Bloomberg, and it highlighted our collaboration with Anthropic. And Anthropic, as you all know, is a leading LLM creator and innovator. And you can see from this article that we expanded our partnership, and TPUs are really a linchpin of this collaboration. And when highlighting the reasons to use TPUs, the CEO of Anthropic mentioned that they're really excited about the efficiencies of TPU, and this has already started to show gains. So this is a fantastic proof point because it's coming from a leading innovator and creator of LLM, and they're increasingly relying on TPUs. So now we're going to take a look at text-to-image use case here for diffusion model. We partner with another leading open source innovator, which is Hugging Face, and we put this really cool demo, which basically takes the text-to-image stable diffusion Excel model and does the inference on TPU v5e. So I'm going to switch over to a live demo. We're going to generate some images with the text prompt, and then we'll come back to the presentation. We're ready now. So I'm going to give it a prompt. Let's see. Take me to All right, so I gave it a text prompt, and it seems that the server is busy here. I'll just refresh it. If it doesn't work, then we'll post the demo. We'll post the link to this demo on the registration page, and you can follow it from there. The system seems to be busy. As I said, we'll post the link, and you can take a look at the demo. So this is the last use case, which is another customer of ours, Assembly AI. And this is a third type of use case. So we saw LLM, we saw the text-to-image stable diffusion, although the demo didn't work, but you can still follow the link and see the incredible images that it produces. So this third type of use case is automated speech recognition and text-to-speech model. So as you can see from here, Assembly saw 4 times greater performance per dollar using our TPU v5e for their production ASR model compared to the other solutions in the market. All right, so we covered the overview of the TPU. We looked at the TPU architecture. We discussed the training on TPUs. We also discussed inference on TPU. We're going to wrap it up on giving you some guidance how you get started. So I'd like to start here, actually. And the key thing to note here is that we provide various consumption models to fit the needs of your business and use case. So you can start with an on-demand. You can spin up, on-demand resources as you need them, which is really great if you have a bursty workload or if you are, testing new workload. But once you know your steady state requirements, you can purchase the committed use discounts for 1 year or 3 years, which helps you get deeper discounts and guaranteed availability of resources. And if you need additional savings and additional capacity, you can always leverage spot VMs, which have the lowest price for and more suitable for bursty workloads and more tolerant workloads. And our customers, they're able to use a mix of these consumption models to achieve optimal price for their business needs. To get started, please visit our website, take the AI readiness check. I'll highly recommend doing that, or reach out to your account teams across the globe. We have also produced multiple blogs where you can learn more about cloud TPUs and their differentiating capabilities. And we have also published multiple user guides and literature with more technical resources on cloud TPUs. With that, it's a wrap. So thanks for joining us today and learning more about our latest innovation in cloud TPU and AI hypercomputer. We'll look forward to seeing you leveraging these innovations to power your GenAI workloads globally. Uh, and now we'll open it up for Q&A. All right, so I see a question here. Yeah, so I'll take this one from Joy. How does the transition from 4x4x4 to 4x8x4 affect networking? So it doesn't actually, because it's still in the same ICI domain. And as I was mentioning before, within the ICI domain, the chip interconnects through the very high bandwidth ICI network. So going from 4x4 to 4x8x4, it doesn't impact any of the networking. I see another question here. How do TPU compare to competing methods of GenAI processing like NVIDIA A100? So I think every use case is different, right? You have to really understand your use case, set up performance benchmarks at what exactly you're looking for. Are you looking for best performance? Are you looking for efficient performance per dollar? So what is the benchmark? What is the use case? And then kind of the discussion comes in about is it GPU, is it TPU, what solution you want to use. But I would actually take it beyond the accelerator. As I was mentioning, that AI hypercomputer architecture, it's not just about the chip or accelerator. It's all about the whole block, right? Your compute, your storage, your networking, your orchestration, your open source frameworks and other libraries that we have produced, like accurate quantized training. So all of this has to come together. It's not just about the hardware. Everything needs to work together to achieve those system level optimization. Otherwise, as I was mentioning before, you're just optimizing at the component level, right? Which basically leads to the bottleneck. So you really want to optimize at the system level. So there's a question from Farhan. Any edge TPU architecture beyond Coral in works? So if I'm correctly understanding, are you asking if TPUs are available in edge? If that's what you're asking? If that's the question, then right now they are not. So TPUs are in our data centers. They are not available in the edge location. But if your question is something else, then you may want to post the clarification in the chat. Okay, I'm reading another question from Joey. How much dollar per chip per hour saving can TPU V5P provide? So when you compare it to our previous generation TPU V4, it provides 2.7x better performance per dollar, which translates into the dollar per chip per hour performance improvement on the previous generation V4. So there is a question from Siam. We have a lot of regression test suites built for the ETL testing. But with the AI in picture, we are thinking of building AI solutions for ETL testing. And for this use case, what LLM should we be choosing? Are there use case repositories for us to refer? Uh, so I'm going to answer this question in a little bit different way instead of answering it which LLM you should choose. Because the first thing is, how do you manage your data, right? In this case, you have massive amount of data, right? So before you even get to a point which LLM to choose and which accelerator to choose, you need to store it in a way which is like you create fast pipelines of feeding this data into the LLM solution that you're going to use. So I think that's step number one here. And once you have organized your data in a way where you can, efficiently create those fast pipelines to the platform, then you can, then you can really implement the LLM models or whatever accelerator um, will work for your use case. But the key here is to create, efficient data pipelines. And that's where, when we were looking at one of the slides, I mentioned it here that we have the efficient storage solution. So we have Fuse storage, we have Google Cloud storage, and we have other block storage solutions that are really optimized for the GenAI use cases. All right, let's see if we have other questions. So one question here is, I'm wondering if there is a benefit of TPU versus A100 when it comes to solving complex finite element problems. Uh, Please comment if you have taken a look at this. All right. So as I was mentioning before, I think it varies from use case to use case, right? And not just that, it's also what kind of optimization you're using, because I talked about a number of optimization that are available in TPU software stack. Quantization was one of them, and many more that we saw in the inference stack, and also multi-slicing and that we have on the training side. So it really depends on what kind of optimizations you're using, and of course on the GPU side there is they have their own set of optimization. So the solution is actually, at the end of the day, what is your use case, what kind of optimization you use, and as I was mentioning before, more importantly, what exactly is your performance metric, right? Because if you're looking for absolute performance, not to make a comparison to GPU, but even to make a comparison with the TPU portfolio, if you are looking for an absolute, performance benchmark, you're going to use TPU V5P because that's the most performant TPU. But if you're looking for, yes, I have a requirement for performance, but I'm more conscious about the cost. I don't want to have a higher performance at the expense of cost. So if perf per dollar is, or performance per dollar is your metric, then you use TPU V5E. So as I was saying, I just draw some comparison between TPU V5E and TPU V5E, but essentially you have to kind of look at it in the same way when you are drawing comparison with the other accelerators. I see one question here, Tarun. How does TPU compare to the recently announced LPU from Grok for GenAI application? So I have to take this question back and do more research on it. I don't have an answer for this now. Do we have any more questions? We just stay here for a couple of more minutes if someone has any more questions. final chance. If you guys have any question, please post it. Give it another minute. Yeah, so I see I think, follow-up question here from Bhagarat, which is data pipeline we can take care of. We have options in all three cloud infrastructure, but my earlier question is specific to choosing the LLM that best fit our use case on ETL testing. So I have to really understand your use case in more detail, but I mean, you can use in our Vertex, for instance, AI model garden. We have open source models from Google. We also have Gemini. We also have open source models from our partners, LLM, Llama. So there are multiple LLM models that are available there. So we have to really look into your use case to see what would be the right model for you. But there are plenty of options available in our Vertex AI model garden, our own first party and third party. Yeah, so there's another question. Any suggestion to test some simple problems on the underlying TPU-based systems? And where can a beginner start for TPU-related sample solution? So the link that we have posted, the resources we have posted on the page, there are user guides in there. And within the user guide, there are actually different, there are sample codes for different implementation of various LLMs. So you can pick it from there, and you can easily kind of replicate that code in your own environment. So that would be the kind of the easy start. There is also actually a Kaggle. If you go to Kaggle, and within the Kaggle notebook, you can actually run the code on TPU. So you have the option to select the TPUs, and there are a number of reference implementations out there. So if you don't want to go through the training guide and do all of that, you can just simply go to Kaggle, and Kaggle already has TPU resources attached to its notebook, so you can start there. So I see a question here from Joey, which is, since V5E is 4x more scalable, should we expect V5 deployment is also going to be 4x? I'm not sure if I understood the question here. So I think by scalability, it was like you can scale it across multiple pods. So from that factor, that was the scalability aspect of it. If you are talking about the deployment cost being 4x higher, maybe that's what your question is. It's actually not. So from that standpoint, if you look at performance per dollar, it's not linear. So it's not like if it is 4x more scalable, is it 4x more expensive? No, it's not. Just give it a minute, otherwise we'll wrap it up. Well, thank you everyone for attending this event, and the recording will be posted on the site as well. So for those of you who want to refer back to this, you can always watch the recording from there. Thanks once again, and bye.
At Google Cloud Next, we're announcing an amazing show.
All right, cue the music.
We're building the new way to cloud.
So that just means we get to think even bigger.
and now helping you connect like never before.
Let's start with development.
I'm loving this. Super cool.
AI is going to change the game for all of us.
Live on the demo stage.
I can't tell you how excited I am to continue blowing people's minds.
We're now in the midst of one of the most profound technology shifts in history. There's so much more for all of us to explore together that'll power this next chapter of digital transformation.